So let's go to the second topic titled The Technical Challenges and Solutions for Asymmetric Ethernet Communication Systems. It will be presented by Mehmet Tazibai from Broadcom. He is Technical Director at Broadcom. He leads innovations and the physical layer products, contributing to industry standards and advocating Ethernet for automotive communication. Today he will present a comparison between different asymmetric high-speed technologies. So the stage is yours.
Thank you. Good morning. It's my distinct pleasure to be here 10 years later again. And 10 years ago, we were discussing symmetric Ethernet architectures, and today we are going to be discussing asymmetric Ethernet communication systems. So, a new demand and opportunity is emerging for standardized asymmetric Ethernet solutions, especially for automotive camera and display applications. There are some non-Ethernet asymmetric high-speed solutions available today in the marketplace. However, some of these incumbent solutions have two important limitations. Number one, they are proprietary. That means they are non-interoperable single source. They also have some limitations for the performance as the data rates increase and cable reach increases. So today we are going to discuss some of the technical challenges of asymmetric communication. And in particular, for the camera application, we are going to discuss the complexity and power consumption for some of the proposed architectures. Any solution to be viable, it has to be standard-based. For that, established standardization bodies such as 802.3 provide a forum where people can effectively study and discuss the respective challenges of solutions. However, at the same time, a full ecosystem is also equally important to be developed. So here is my agenda. First, we are going to discuss some of the challenges of automotive communication systems. Automotive EMC is a critical topic which contributes to overall total cost. And data communication techniques are proposed for various high-speed asymmetric solutions that we are going to take a look. Then we will discuss existing and upcoming standards, including 802.3 DM proposals. The vitality of automotive Ethernet ecosystem is critical. That's something that we are going to touch base before we close the presentation with a summary and conclusions. As the channel attenuation and noise impairments increase with the increasing frequency data rates, there is an impact on the PHY performance. Lower performance means more susceptible to EMC immunity for the PHY. So there is a trade-off that can be attained by increasing the transmit signal levels, but that can be an issue for emissions as well. Therefore, innovative designs are required for the PHY to compensate for this loss. EMC in-cars is particularly challenging. Typically, the in-car results are quite different than the lab results. There is a well-known 1000-base-T1 UTP case. It worked in the lab, but not in the car for some use cases, especially for the FM and DAB band. So therefore, achieving the best EMC performance is the key. While optimizing for a robust EMC, the solution must be cost competitive as well. EMC validation is a critical topic for automotive applications. There are 3 stages of testing that happens for the EMC. IC level testing without the connectors and cables. And second one is the component level testing with the cable and connectors. And third and most important one is the in-car system level testing for radiated emissions and immunity. So proper design constraints must be put in place for the PHY in order to get the higher success for the passing results for the EMC in-car. Typically, silicon vendors concentrate on the IC level or component level testing, but these are the intermediary steps for EMC performance verification. They are the necessary conditions, but not the sufficient condition. The final judgment on EMC performance is typically in-car test results. Recently, the effect of aging of the cables segment is shown to be severe. So EMC conditions can change over time. Any PHY with weak EMC performance can cause increased costs for the, for example, camera application. Additional measurements have to be taken for the shielding measures that have to be taken for the camera application, which increase the cost of the module, for example. Therefore, it is necessary to optimize and design the PHY for the best EMC performance to minimize the risk of failure or minimize the cost of the overall system. Now, let's take a look at some of the data communication techniques proposed for asymmetric PHY solutions today. So the classical approaches are TDD, FDD, or full duplex. These are widely used for different applications, such as cellular and wireless, but also recently, ASA Motion Link adopted the TDD for its duplexing technique. Most incumbent solutions, on the other hand, using automotive SerDes solutions, for example, is using the FDD, while 802.3 Ethernet PHYs mainly exclusively use full duplex communication. There are pros and cons depending on the spectral efficiency, interference handling, and hardware complexity of these different techniques. TDD was proposed to 802.3DM as an asymmetric PHY solution. TDD periodically alternates the downstream and upstream solution such that it's not affected by echo, thus providing a good performance margin without the need for a complex sharp filter on an echo canceller. The same SerDes PHY can be used for the both camera and ECU side, and configurable TDD allows symmetrical and asymmetrical data rate by just changing the duration of the TDD. The second modulation scheme proposed for 802.3DM is called asymmetric concurrent transmission, which is ACT. ACT is not FDD. FDD has a small frequency overlap, while ACT has full spectral overlap of two transmit directions and using different modulations for upstream and downstream. For upstream, differential Manchester encoding is used similar to 802.3CG, 10BASE-T1S, while downstream is using PAM2 modulation. The time and frequency overlap of the ACT causes echo signal. Performance loss can be observed without the echo cancellation and may need higher order filters. ACT addresses this issue by increasing the TX peak power for the upstream. However, this can cause in-car emissions potentially, so this needs to be paid attention to. So when comparing different communication schemes, the modulation scheme and the duplexing must be considered. The input dynamic range of the PHY includes the received signal plus noise impairments. Various signal processing techniques are utilized to maximize the SNR to achieve the best performance against EMC. Since there is no echo interference in the half duplex TDD case, more SNR margin can be attained. If there is no echo cancellation in the ACT case, there can be less margin. But however, if there is echo cancellation, then similar SNR margin can be attained as well. Now, let's take a look at the camera PHY receiver complexity. Camera PHYs are important from integration point of view between the sensor and the receiver. So this was extensively studied and discussed in 802.3DM, and two different architectures are shown here. On the left top, we are talking about the TDD PMA architecture, which is using an equalization scheme and a timing recovery, which handles the sampling point of the ideal signal. And also, a sample layout is shown, which is tiny compared to other blocks in the receiver. For ACT side, a simple DME detection circuit is used, again, without the echo cancellation being shown. The area for the camera receiver is pretty much similar between TDD and ACT, which is about 0.012 millimeters square for both of them, and the power number is about 3 milliwatts. So in other words, the PHY implementation, PHY receiver implementation for the camera can be feasible and also cost-effective for both TDD and ACT. However, the camera PHY is not only PMA. There are other digital blocks such as FEC, PCS, and also there is EMC protection in some of the cases. EST is also another block that occupies area in the PHY. But overall, this small area, 0.012 millimeters square, is still much smaller than the camera sensor, which is about 40 millimeters square. So in summary, it is feasible to integrate the PHY camera receiver into the sensor very easily with these architectures. One question is, why is TDD PHY receiver is so small for the camera and ECU? Removing the effect of the echo signal from the TDD PHY allows us to use the conventional 10 gigabit analog SerDes technology. This technology has been developed over more than 2 decades ago. The plot here shows the 8-port 10 gigabit analog SerDes scaled down significantly from 2000 to 2013, and the area and power is drastically reduced while the channel conditions are worsened. So in other words, the performance increased, but the area and power has been decreased significantly. So if you are to look at the 28 nanometer in 2013, the power for 8-port is about 50 milliwatts, and the area is 0.23 millimeters square. So if you scale it down to 1 port, the area is about 0.03 millimeters square for the camera receiver, for example, which is in line with the analysis that was shown in the previous slide. So in other words, the further area and power optimization can be even achieved using the latest implementation techniques. So now let's take a look at the existing multi-gigabit automotive imaging solutions. This list is by no means complete. There are different solutions available, and 2 of the solutions on the left is showing GMSL 2 and 3 NFPD link are the proprietary solutions. And these proprietary solutions and some of the existing solutions on the right-hand side standard is changing the data rate, line rates from 2 gigabit per second up to 16 gigabit per second. Most of the techniques are using FTD, except TDD is being used for ASA. The reason for that is, again, to use the effective analog signal SerDes techniques without echo cancellation. So echo compensation is an important factor which is not applicable to TDD. Channel length is about 15 meters for all the use cases except the proprietary solutions. That depends on the EMC performance and the data rate. Now let's take a look at the existing versus upcoming standards. Again, this is not by all means complete standard solutions. There are other solutions available in the marketplace. This table shows one important factor. The market is very much fragmented. There are many solutions available, upcoming standard solution and existing solutions, which creates some confusion in the marketplace from OEM perspective because there are so many solutions to choose from. So there are 3 important factors in this table. One of them is the EMC is critical for an upcoming standard solution. And second one is the ecosystem, which should be available to deploy any given technology. And third one is the multi-vendor availability. Both of these techniques, TDD proposal or ACT proposal, are technically feasible. However, the difference is in these factors that I just mentioned. So here are some of the proposal pros and cons and differences. It's not easy to compare different solutions side by side, and it's a sensitive topic to do so. So I will try to highlight some of the differences and similarities as unbiased as I can be. But the point is, duplexing method at the PMA is one of the differentiating factors because TDD has no echo and ACT has echo using a concurrent transmission. Power or coax is feasible for both solutions, for both TDD and ACT. And both solutions can operate without a crystal on the camera side. FEC complexity is low on the camera side for both of them. However, it's slightly higher on the ECU side. And EMI risk is lower for TDD because non-overlapping signals and wideband signaling allows less of the signal transmitted and received. And finally, in-car EMC results are available based on ASA motion link based on solution. PHY usage is another important factor for choosing different solutions. Same SerDes PHY can be used for both sides of the camera and ECU for TDD. However, different modulation techniques are used for the ACT. DME for the upstream and PAM2 for the downstream requires two different PHYs. Camera side complexity is low for both implementations, and same thing for the power and implementation cost of the camera as well. ECU side complexity, on the other hand, is slightly higher based on the signal processing technique that's being used for the ACT. Ecosystem is important, and it's fully developed and leveraged from ASA Motion Link. And multi-vendor interoperability is also something important. For TDD-based PHY, it is provided from the ASA Motion Link again. So one important factor is the automotive Ethernet ecosystem. Open Alliance was formed to quickly develop a necessary ecosystem and complement 802.3 base T1 PHYs. Various technical committees existed for addressing automotive industry requirements and needs. There are today at least 10 silicon vendors for supporting base T1 PHYs. What is in the ecosystem? Ecosystem is not only a physical air transceiver, but test houses for conformance, interoperability, and EMC testing, and as well as test equipment manufacturing. Finally, multi-vendor silicon availability. So industry can utilize this ecosystem from ASA possibly, and this is a strong commitment where the industry can benefit from. Finally, here are some conclusions and summary. We are seeking a cost-effective and high-performance Ethernet-based solution for asymmetric automotive imaging systems in 802.3DM today. EMC complexity and power should be optimized not only on the camera side, but also on the ECU side as well. Since there is no echo, and only because there is no echo, the half duplex system allows us to implement well-established low-cost analog signal processing techniques for high-speed communications on both sides. ASA Motion Link TDD solution, as I said, is leveraged and optimized for 802.3DM for a single PHY solution. With the echo cancellation, ACT proposal can achieve good performance as well. But without echo cancellation, at least in our analysis, that can be an issue for the implementation. So finally, the total cost of ownership must be considered and optimized. A single PHY solution needs to be aimed for wide adoption and easy interoperability. A readily available ecosystem is critical for any successful technology development. With that, I thank you for your attention.
Thank you for the presentation. So, any questions?
A quick question. Over here. Hi. Thank you for this presentation. I can't believe 10 years have passed. I guess I remember the 802.3 BP presentation you did, a decade ago. Just a quick question on EMC. I think I also hear feedback that EMC is important. Do you see a pathological case? As designers, how can we design a car if basically if you're detecting a failure at the very last stage, you're doing in-car testing? Do you see pathological cases now based on your decade of experience in this business? And how would you compare these proposals, and maybe you did this already, how would you compare TDD ACT to 802.3, the fully symmetric technology? Could we expect EMC to have a better time for both, or could we, what do we expect, I guess?
So, yeah, thank you for the question. I think one of the lessons learned from 1000-base T1 was, I think it's in this slide, the design is as good as the assumptions. In other words, if you make the right assumptions for the implementation, then EMC can be a solvable problem. The problem that we had for 1000-base T1, for example, we assumed a spectral PST, power spectral density function for the 1000-base T1, which caused emission later on because it didn't meet what was actually happening in the car. So there was an overlap between the FM and DAB band and 1000-base T1 signal. So answering your question, it is rather important to put the constraints in the right place where the EMC can be constrained properly. So between these two techniques, I think important thing is to add the proper constraints and design the system accordingly.
Okay, thank you.
Thanks.
I can take it, right? Mehmet, thank you very much for the presentation. It was nice. I have a quick question. Do you have numbers for the efficiency loss because of the time synchronization problems that may happen? Some numbers, some measurements do you have already available?
For emissions?
Oh, no. Efficiency decrease because of time synchronization or guard time, you know.
So, yeah, it is about the latency and efficiency, and it's well, defined in ASA, which we are trying to leverage for, 802.3DM as well.
Okay. But there are no numbers or measurements?
The numbers are provided in the ASA, and also 802.3DM it's being considered, but I don't have it from the top of my head.
Okay. Thank you very much.
Okay, thanks.
Hi, Mehmet. Thanks for the presentation. So my name is Amir Barniv from Infineon, and I'm representing the other camp, okay, that is doing ACT, okay, versus the TDD. And I have to say that I'm really surprised by your presentation because there are many things that you show as facts, okay, when you compare TDD to ACT that contradict about 80% of the presentation that I've seen in 802.3DM, okay? To start with, you forgot to mention that ACT use 100 meg receiver inside the camera, while TDD use 3 gigabit receiver, okay? And you repeating your claim that 3 gig receiver and 100 meg receiver are either same size, or even you said that 3 gig is even smaller, okay? I guess based on this rationale, maybe we should do the uplink 10 gig because it will be even smaller than 3 gig, okay? I don't understand this argument, how 3 gig receiver can be smaller or same size as 100 meg. You claim that crystalless is feasible for TDD and ACT, okay? The only issue is that ACT, it's already silicon proven that it can be crystalless. TDD, there is some presentation, okay? And obviously, to keep TDD as crystalless is way more complicated because you have the receive clock only 10% of the time, okay? So you need to implement a much bigger either PLL or use a crystal. In any case, it was never proven yet on a real silicon with TDD to be crystalless, okay? I never seen any claim of that. You talked about EMC. Obviously, EMC is very important. You say TDD passed EMC requirement in car, ACT not, okay?
Not yet.
Not yet, exactly. Well, the reason is, again, you forgot to mention, is that ACT only exists for, you know, a few months in the market. You know, ASA or TDD exists for 2 years, so
Right.
we already did the testing on ACT for system level, and you know it because we showed it in IEEE 802 3DM that passed all the tests. We are going to do it in in-car, and we have no doubt that it will pass. So when you compare the two solutions, okay, you also didn't mention the complexity of the state machine of TDD compared to ACT. So I guess I'm trying to understand if this presentation, okay, is a real comparison that based on facts or on wish list thinking. I'm a little surprised by this presentation.
Yeah, let me start addressing the complexity first, okay? As I said, for Hell2Plex Phi, it's a well-established technology for more than 2 decades, right? I mean, today we are talking about, this is why I said in this slide, the area that was shown, and this was a sample layout that was done actually in the actual circuit, it is 0.012 millimeters square just for the camera receiver. On the other hand, if you look at the 10 gigabit SerDes technology in 2013 in 28 nanometer, it is about 0.03 millimeters square for this entire single port. So this is in line with the architecture that was discussed in IEEE. So removing the effect of the echo signal from the TDD problem allows us to use the conventional 10 gigabit analog SerDes architectures. That's why, you know, it is being discussed extensively. That's the reason that I want to give this example, and this is actual circuit implementation in production. So that's the complexity question. Regarding to crystalless, I mean, ACT and TDD, we can get into discussion on this, but as I said, in theory, for both of them to be possible to operate without a crystal solution. So I think from technology perspective, we can discuss, but I think both techniques can be doable. However, I think the fundamental issue is taking advantage of such as ecosystem availability and few other things to be considered from ASA side. And you mentioned a lot of points, and we can take this offline and discuss, because I think there are important topics, and they need to be discussed in addition to what can be done in IEEE as well.
Okay. So I guess my only comment is that you mentioned again and again that ACT need echo cancellation. Okay, we have a silicon today that is proving that there is no echo cancellation needed, either on the camera side or on the switch side. Okay, and this is silicon proven that meet all the requirements on the performance and all the EMC measurement, both for emission and immunity.
Yeah, one thing I would like to add there is basically there is a certain return loss requirements, which is very low in order to meet the no echo canceller information, right? With the high return loss limit lines, there can be an echo problem. At least in our analysis, that's what we see. But I believe that increasing the peak power of the upstream, DME upstream, you can get there without the echo canceller. So I believe that. But however, that requires very good channels with good return loss.
Let's take it offline. Thanks.
Okay, thank you.
Other questions? Okay, so thank you.
Thank you.